Okay, so to recap what we just did for our online friends, online students. So can the sum of infinitely many numbers be a finite value? We discussed this and we said the answer is yes, it can be. And for the simplest example, I can give you something like 0.333, etc., because you can write this as 3 over 10 plus 3 over 100. That represents this decimal, right? Plus 3 over 1,000. Plus, etc. So you could add up infinitely many of these numbers, these fractions, and it will end up to be one single finite answer, which we usually represent by a repeating decimal like 0.3 with a line on the top. And we also talked about the square that was one side is 1, the other side is 1. And we talked about the fact that if you cut the square into pieces, like first half the square, this side is 1, this side is a half, the area of that piece is a half. Take half of the remaining half, that area is going to be a quarter. Take half of the remaining half, that's going to be an eighth. We add them up, but we know that the total should be the area of the square, which is a finite quantity, and that finite quantity we discussed has an area of 1, because the original question was a square with 1 on each side. So yes, the answer is yes. You can add up infinitely many numbers and get a finite value, but the catch is the numbers you add must be very, very small. And hopefully they're getting smaller and smaller as n goes towards infinity. Like the case is here, these numbers are getting smaller, and these numbers are getting very small as well. Okay, so today we're going to take a look at infinite series. First, a basic definition. We learned about sequences so far. A sequence is basically a listing of elements. Like if I write the numbers like a half, comma, a fourth, comma, an eighth, comma. Okay. As a sequence, I would write it like this. As a sequence, this is 1 over 2 to the n, correct? As n goes from 1 to infinity. We just talked about this, as a matter of fact, right? That's a sequence. Okay. Now, what is the limit of the sequence? What is the limit of the sequence? As n goes to infinity. In other words, where does the terms approach of the sequence, like a half, a fourth, an eighth, as n goes towards infinity, what is happening to each and every term? Take a limit of this. Limit as n goes to infinity of 1 over 2 to the n. What is the answer? 0, right? So the sequence is going to 0. But if I do the following, I write a half plus a fourth plus an eighth, etc. Does that go to 0? We just did that one, right? Think of the square example. We added those numbers. The sum of these numbers is not 0, right? So there is no difference between a sequence and a series. A sequence only looks at the individual numbers and looks at what is the trend for the individual numbers. In this case, the trend is they're going towards 0, so the limit of the sequence is 0. Okay? But how about the series? The series is what happens when you're adding the sequence. So add these terms, and what do we know about that sum? We just did that one, right? That's your square problem. So if you're adding all these numbers, the sum was, what was the sum of these numbers? It was exactly 1, right? It's not 0. So the limit of the sequence is 0 because individual terms are approaching 0. But the limit of the series, the sum of these numbers, what is that? That's a totally different value. So it's a very common mistake throughout this chapter. The very big danger, I'm telling you right now so that maybe you can avoid it, is to confuse between the limit of a sequence and the limit of a series. The sequence is only looking at individual elements, or basically the listing of the terms. So here you have a sequence right here. But the moment you add them up, you're looking at a series, and the limit of a series is basically the sum of infinitely many terms of that sequence. The sum, that certainly is not going to be the same thing as the limit of the sequence. Now let's look at the formal definition. Here it is. As infinite series is basically the sum of a sequence. It is the sum of a sequence. And in compact form, we usually write it like this. Summation as n goes from 1 to infinity of a sub n. And in expanded notation, that would represent a sub 1, a sub 2, a sub 3, and so forth. Okay. Now, anytime you deal with infinity, basically you need calculus. Because this is why, the ancient mathematicians, they couldn't take the leap. Like they found the area of a circle where it was inscribed by a polygon of 96 sides. But they just couldn't take the leap saying, let the number of sides of the polygon go to infinity. Because they didn't know how to take a limit. They didn't have any idea about how to deal with infinity. So they stopped at 96 sides. So again, today we know much more than that. You can't let n go towards infinity. So anytime you have an infinite sum, know that the way we're going to handle that is through limits. So we're going to redefine this now as follows, okay? First, we define something called the kth partial sum. Very simple concept. All you do is you add up the first k elements. So here you had infinitely many elements, right? Now, the kth partial sum is you just add up the first k numbers. For example, if I'm talking about the third partial sum, s sub 3, then you would add up the first, second, and the third terms of your sequence. That's your third partial sum. Why do we have to define this? Well, because infinite sum can't do, but limits, yes, we can. So we're going to define this infinite sum as a limit. It is the limits of the sequence of partial sums. So this infinite sum can be written as the limit of its partial sums, and another way to write it would be the following. Limit as k goes to infinity of the partial sums. Now let's try to understand what is meant by this by doing an example. Okay. Write the first 5 partial sums for 1 over 2 to the n, the summation of 1 over 2 to the n, and then estimate the sum. Yes. You want me to scroll down? Yes. So once again, we define an infinite sum. As a limit. You see what happened here? First, we summed up the first k elements, and then we took a limit as k goes to infinity. That's what we did basically, okay? So again, anytime you're dealing with infinity, you got to bring in the limit tool, because that's the way to handle infinity in calculus. That's exactly what we're going to be doing. So for example, in this example, we want to write the first 5 partial sums for summation 1 over 2 to the n. Let's start with s sub 1. S sub 1 is very easy. You just take the first term of the sum, which is what? 1 over 2 to the 1, right, which is a half. Okay, what is s sub 2? Take the first, again, by our definition, s sub k is called the kth partial sum. So s sub 2, that means add the first 2 terms now of the series. So 1 over 2 to the 1 plus 1 over 2 to the 2. So what is the answer there? As a matter of fact, I want you to do this for the first 5 partial sums. Do s sub 3, s sub 4, and s sub 5. Let's see if we can look at those and estimate the sum. So it looks like s sub 2 is 0.75, right? So what do we get for s sub 2? 0.5 plus 0.25 or 0.75, right? Okay, how about s sub 3? Add up the first 3 terms, right? And what do we get there? Is it 0.875? Did anybody do it? Okay. How about S sub 4? Now you're going to add up 4 terms, right? Actually, we'll get the idea there. We might stop at that point. You got 15 over 16 for that? If you simplify, that's a good approach. Just get common denominators. And as a decimal, what is that? Somebody with a calculator, can you tell us? 0.9375. Did anybody do S sub 5? To this number, add 1 over 2 to the 5th, like 1 over 32. Right, 2 to the 5 is 32. So we're getting like 0.969, something like that. The next one is 0.969. So what you see here is called a sequence of partial sums. S sub 1 is the first sum. S sub 2, adding the first 2 terms, adding the first 3 terms, adding the first 4 terms. You see how we created a sequence out of the sum? And now if you take the limit of that sequence, you will have the answer for the infinite sum. Any guesses what that answer might be? Look at these answers. 0.5, 0.75, 0.9875, 0.9375, 0.969. Any guesses where they might be approaching towards? They're increasing, but they're not increasing that much anymore because you're adding ever so slightly a number much, much smaller than the past number. One guess was 1, perhaps the limit of, so we're saying that maybe the limit of S sub k, the limit of the partial sums as k goes to infinity, perhaps it's equal to 1. It's at the moment just a guess, right? But didn't we already solve this problem earlier? Wasn't that our square problem here? Look at it, a half plus a fourth plus a third plus 1 over 16, right? So we're doing it a few different ways today. One way we did it was geometric way. Now we're doing with sequence of partial sums. In a minute, we're going to do it with a formula, geometric series formula, okay? So the answer will indeed turn out to be 1. Now, this next example is really interesting because most people will get this one wrong if they did not have some training in infinite series. Like, if you just ask an average person, what is a sum? Because it doesn't look that complicated. You know, it doesn't look like you need to know calculus to do this problem. Think about it. Can you give me the first 3 elements of the series if you were to list them out? Like if n is 1, what do you get? Negative 1. If n is 2, 1. If n is 3, right, negative 1. Just want to get rid of the last one there. Negative 1. Basically, it goes on like that, right? The average person might say the answer is 0, right? But let's see why it's not 0. Now that we are students of calculus, right? Let's see, it's not really 0. That's the tricky part. Okay, how do we define an infinite sum? Always through limits, okay? It's a limit of a partial sum. Let's start writing the partial sums. What is S sub 1? The sum when you add up just the first element. That's negative 1, right? Okay, what is S sub 2? Add up just the first 2 terms now. Negative 1 plus 1, which is 0. What is the third partial sum? Let's see. Negative 1 plus 1 minus 1, which is negative 1. And I'm just going to write a couple more. S sub 4 will be 0, and S sub 5 will be negative 1. So these are the numbers we're getting. This, 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 and this. Now compare it with the answers we got up here. Up here we had 0.5, 0.75. These were approaching somewhere, right? They were all seemed like they had a mission, right? They were going towards to a unique number, right? Whereas in this new problem, do they seem to have a mission to be approaching to a unique number? No, they're fluctuating, they're oscillating, right? So what can we say about this limit of the partial sums, limit of S sub k, as k goes towards infinity? Because that is the answer to the original question. And that limit does not exist. So therefore, the original sum does not exist. And if you think about it, you know, we don't know if infinity is even or odd, and because it's neither, it's a weird phenomenon. It just means, you know, you're repeating this process many, many, many times. So you don't know where you're going to stop. And we can clearly see there's no pattern here. The numbers are not going towards a unique number. So the correct answer is the limit does not exist. Okay, now we're going to look at what I've been promising all along, the geometric series. And here is the definition. So it's a specific type of series. So far, all we've learned is that a series is the sum of a sequence. And how do you find an infinite series? Through looking at the sequence of partial sums. Okay, now we're looking at a specific type of series called the geometric series. And basically, the definition is the following. The summation of a times r to a power as that power goes from 0 to infinity. And if you write out the first three elements, this is what you get. The first term, when n is 0, you get a. Plug in n equals 1, and what do you get? A times r to the 1, that's ar. Plug in n equals to 2, and what do you get? A times r squared, right? And so forth. So this is the expanded version. The other one is the compact version for the geometric series. This is actually called a geometric series with a common ratio of r. Why is that common ratio r? Think about it. Going from one number to the next, what are they multiplying it with to get the next one? They multiplied it by r to go from a to ar, right? Okay, at the moment I'm going to cover half of this because I want to make sure that you guys are with me. So to go from ar to ar squared, they still multiply by r, right? And from here to here, they still multiply by r. Therefore, there's a common ratio, and the common ratio is r. Okay. Now, there are very shortcuts, very simple formulas to find an infinite sum, which is of the form of a geometric sum. So this is the first one. If you have a finite geometric series, a finite one, finite meaning you're going from 0 to k, not to infinity, but to a finite answer of k. In other words, ar squared, ar cubed, all the way to ar to the k. This is the formula. If I have time later today, I'm going to come back to prove this formula. If I don't have time, please know that there are lecture notes available on the website. For the first two sections, sequences and series, there's some written out, typed lecture notes available. Just go to where you normally find the videos. It's right there. And in the lecture notes, I have actually proven this. Okay, so if I don't have time to go over the proof, it's really neat. I hope that you'll take the time to take a look at that. So the first box here that we have is the formula for the sum of a finite geometric series. Now I'm going to show you the formula for an infinite geometric series. As a matter of fact, I'm going to have you guess the next formula from this one. It's really not that hard. I'll guide you through it. Okay, if this is up to k, you're adding the first, from 0 to k. Now we want to do infinite sum, right? Now think of it almost like a partial sum, s sub k, right? You add it up to the kth term. To find the infinite sum, you need to take a limit as k goes towards infinity, right? Now assume r is a number that is less than 1. Okay, say assume r is something like a third, a fifth, a number between -1 and 1 is less than 1. Think of it as a third, just to have a number in your head to represent r. R is a third. Okay? Now you're taking a limit of this quantity on the right-hand side as k goes to infinity. Because to find the infinite sum, you would have to take a limit of the kth partial sum, right? So take a limit of this quantity as k goes to infinity. Where does this go as k goes to infinity? Think of this like a third to the k, and k is going towards infinity. So where does that go? 0. How do you know that? This was one of our special limits, right, for the sequences. That goes to 0. So if that part goes to 0, that's going to completely disappear. So that means the infinite sum will have the answer of a times 1 divided by 1 minus r. Let's check that. Let's check that. The infinite sum has exactly what we thought would be. It has that sum. So the first one is the finite sum. And if you take a limit of that as k goes to infinity, and you have to put an assumption that r is less than 1, absolutely r is less than 1. With that assumption, you have a formula for an infinite geometric series. And if you don't have that assumption, if r is greater than 1, then the series diverges. It will not go a unique number. By the way, this term divergence is going to come up a lot in this chapter. So I want you to really, really understand what we mean by that, because we usually mean two things for divergence. Any guesses what divergence means? It's not going to a unique number, right? So there are two ways something can diverge. One is if the numbers are getting larger and larger and larger, it diverges to infinity, let's say, okay? Another way is if they're oscillating, like 0, 1, 0, 1, 0, 1, 0, 1, that's another example of divergence, okay? So ultimately, they're not going to a unique finite answer, then that means it diverges. So if your r, or the common ratio, is greater than or equal to 1, there will be no answer. There will be no finite answer. Only if r is less than 1, you're going to have a finite answer for the geometric series. Now let's do some examples with this rule. So again, if I have time, I'll come back to the proof. If not, please take a look at the proof from the lecture notes that are on the web. Okay, let's do some examples. We're going to evaluate the given geometric series. Let us start with something very familiar today. We're going to revisit the same problem for the third time. And the problem, as you may have guessed, is a half plus a fourth plus an eighth, etc. First, we did this problem with the geometry approach, right? This was, half of the square plus the other quarter of the square, plus we kept adding more and more pieces of it. And we knew the answer was what? What was the total area of that square? 1. So we knew this answer was 1 from the geometry approach. Then we did the sequence of partial sums. What answer did we guess for the answer there? 0.5, 0.75, 0.875, 0.9365, right? It was still going towards 1, right? Now here is a third approach. We recognize this as a geometric series. And it's an infinite geometric series. The formula says a over 1 minus r. And a represents the first term, and r represents common ratio. Okay, so in this case, the first term is a half. And what is the common ratio for this question? Going from here to here, what did they multiply this number with to get this number? 1/2, right? Going from here to here, same thing. So the common ratio is a half. So on the bottom, I'm going to put 1 minus a half. So what are we getting as an answer? A half divided by a half. Nope. This one, right? Same exact answer, but this time we did it differently using geometric series approach. Okay, another example. Can you do the following? Summation. So let's call this example 1. Example 2. Find the sum of this series. Summation n from 0 to infinity of 5 times 1 over 3 to the n. Think about it a little bit, and then we're going to discuss the answer. Any thoughts? First of all, do you think this is a geometric series? If you have any doubts, start writing out the first few terms. If n is 0, we get 5 times a third to the 0, which is 1, plus, if n is 2, what are we getting? 5 times, if n is 1, we get 5 times a third, right? If n is 2, 5 times a third squared, etc. It's going like this, right? So what is, does this look like this geometric? Yes. And what is the common ratio? 1/3, because going from one term to the next, they multiplied by a third. They did the same thing from here to here. It's a constant of 1/3. That is our r. So to write this sum, I'm going to say, okay, based on the formula we just learned, a over 1 minus r. So my a is 5, and my r is 1/3. I'm getting 15 over 2 for the sum. How about you? Okay. Now, what if you don't start right at 0? So, for example, say that we had another example. Say you have summation of n from 2 to infinity of say 3 times 6 over 7 to the power of n. Yes, n from 2 to infinity. So once again, we could write out the first few terms. The first term is 3 times what? 3 times 6 over 7 to which power? Since the lower index starts at 2, we need to start our summation with a power of 2, right? 6 over 7 to the second power. Okay. Plus 3 times 6 over 7 to which power? We just keep incrementing by 1, right? Okay. Now, there are several ways to do this question. One way is the easiest. The other one's a little bit more work. They will all give you the same answer. Any thoughts how you would do this one? Yes, Chris? What did you use for your A and R? I think you have the shortest shortcut method in your mind. That's why you're saying just to. So what is the shortcut method, which is? Right, as long as you go with that A is the first term, so take everything 3 times 6 over 7 squared, divide by 1 over 1 minus r. But some students, because they took pre-calculus in the past and perhaps with a different professor, some students, they say, okay, no, wait a minute, A is not that. A has to be 3, or they have this conception of A cannot be the first term. So let me show you something. You could actually factor out, so I'm going to do 2 ways, okay? Now you choose the way you prefer, okay? One way to do this problem is factor out a 6 over 7 squared. 6 over 7 squared. What is left in your first term? 3. And in your second term, 6 over 7 to the first, right? And the next one, 6 over 7 to which power is remaining? If you take the second power out. Yeah, I didn't take the 3. I was debating whether to take the 3 or not, but the 3 is still there. It's going to be in each term because I didn't take it out. Yes, thank you. So the 3 is still in there. 3 times 6 over 7. 3 times 6 over 7 to which power for the next term? Squared. Because I'm here now, I took out the second power, 6 over 7 to the second outside, left over 6 over 7 to the second power, and then it goes on like this, right? So now those students might say, okay, now I know my formula works with this one. I know my formula works over here. And what is that formula? A over 1 minus r. What is A here? Okay, A is 3. The traditional A would be 3 over 1 minus 6 over 7. That's the common ratio, right? The number that you use to go from one term to the next, you keep multiplying by that. Now let's simplify this complex fraction in the brackets. Let's see what we get there. So you have 7 minus 6. I was showing you two ways to do this problem. I'm also going to do it the other way, okay? So here we have 3 divided by 7 minus 6 is 1 over 7, which is the same as and let's see what we got with this approach. Six over 7 squared times 21. I'm getting roughly 15.43. Okay. What did you get if you did it the other approach? If you assume that this is your first term, this is your A, so the sum of infinitely many terms equals A over 1 minus R, and A is 3 times 6 over 7 squared divided by 1 minus R. R is 6 over 7. So we're going to get the same thing. I can already see it. Let's do it. The bottom is 7 over 7 minus 6 over 7. That's 1 over 7, right? Flip it over. And 3 times 7 is 21, so we're getting the same thing. Okay. Same answer, 15.43. Did anybody get it as a fraction? William? 108 over 7? Okay. Either way, either this or decimal answer is fine. The reason I showed you both ways is because some people who took pre-calculus in the past, they've done it like the way I did it on the top, and they're wondering, how could A be the first term? But you've seen when you have an infinite geometric series, you can do this. You can assume A is always whatever it is your first term. You can use that. But if you have a finite geometric series, you cannot use this shortcut approach. You have to do that factoring, and then you have to use that longer formula that we have there. And we are going to do one finite geometric sum as well. Let's do this one. An example of a finite geometric series. Okay. Go ahead and do summation n from 0 to infinity. I'm sorry, finite. N from 0 to 20 of 5 times 3 to the n. Before we do that one, can you look at the following real quick? 5 times 3 to the n as n goes from 0 to infinity. What would this one be? You don't need to do any math for this one. Just look at it and see what the answer is. An infinite sum where your r is greater than 1. Like you're adding 5 plus 5 times 3 plus 5 times 3 squared, 5 times 3 to the third. Numbers are getting larger and larger and larger, and you're adding infinitely many of them. Any guesses what the answer will be there right away? Infinity. When r is greater than 1, the infinite sum, if you're adding this infinite sum, it's going to be infinity. But the finite sum, there's no trouble with that, right? With the finite sum, as long as you're adding finitely many numbers, no matter how big they are, it's always going to be finite, right? As long as you're adding finitely many numbers, it's always going to be finite. So this is let's write out the first few terms. When n is 0, we have 5 times 1. When n is 1, 5 times 3. When n is 2, 5 times 3 squared, etc. Is this a geometric series? And let's write the last one since it's finite. The last one is 5 times 3 to which power? 20. Now look back to that formula for a finite geometric series. And I'm going to show you that from the notes. Let me bring it back up. This is the formula for the finite geometric series. It has to be exactly in this format. Here, you cannot assume A is the first term. It has to be like A plus AR squared. For a finite geometric series, A is just that number in front of R to the n, okay? And then the formula says let me write the formula here for your convenience. It says a times 1 minus r to the k plus 1 divided by 1 minus r. So here, what is our a? It's in that nice format, so we don't have to factor out anything. A is the 5. On the top, you're going to want 1 minus r to the k plus 1. What is k plus 1 here? 21 divided by 1 minus r. Now you might say, wait a minute, the bottom is negative. Is this going to be a negative answer? No, because the top is negative also, and the ratio of two negatives will give you a positive. So let's just quickly calculate this. .62, 10 to the 10, something like that. It's going to be some very large number, and I know you can get it, but it's still a finite answer, okay? Okay, there's one last thing that I have to show you. I'm going to take the next 2-3 minutes to do this. So you can do some more of your group activity and your homework. It's a very simple test. This is the last thing in this section, and you can always go back and read this also from the book. It says the following. It says the nth term test for divergence. It says if the limit of a sequence is not 0, then the summation of that sequence will be divergent. If the limit of the sequence is not 0, then the summation of that sequence will be divergent. And the problem with this is people get very confused. This is an if-then statement. It goes like this. If this is true, then this is true. But some people think it's a double-edged sword. It's something where you can go this way and the other way. No, you cannot go the other way. If the limit is not 0, then the series diverges. But you cannot say if the series diverges that the limit was different than 0. You cannot say that. So let's do a very quick example of what we mean by this. Say you have summation of 2n over n plus 1. The question is, you don't have to tell me the sum, because this is not geometric. This is going to be a difficult one. All I want to know is, does this converge or does it diverge? Is the sum finite or is the sum infinite? And this test tells you, just look at the limit of the sequence portion. Just look at this limit. 2n over n plus 1. What is that limit? 2. It's different than 0, right? So what does this test tell you then? Then the summation diverges. What does that mean? The sum is not going to be a finite answer. And think about it. If you are adding, each of these is about 2. You're adding infinitely many 2's to each other, the sum will be infinite as well. But what if you had something like this? This is the tricky part. Say you have 2 over n plus 1. What is the limit of 2 over n plus 1? It's 0. Now, can you say then the series converges? Remember I said this is not a two-way street. This is not a two-sided argument. If the limit is equal to 0, basically you cannot say anything. We're going to say no conclusion. You have to wait until next class to have a conclusion for that one. So at the moment, all you can say is if something is divergent. And how do you say it? If the limit is not 0, then the summation of that will be divergent. But if the limit is 0, it could converge or it could diverge. We just don't know. We got to do more work about it, okay? Then the test will fail. All right, let's take a look at a few more examples for the nth term test for divergence. Again, this gets a little bit tricky, believe it or not, because of the way it's worded. It only works one way. In other words, if the limit is not 0 for the sequence, then the series diverges. But it doesn't say anything about if the limit is equal to 0. In other words, it says limit. Let's go back to the definition. Limit is different than 0, then it diverges. But it doesn't say that this way. It doesn't say that if it diverges, then the limit must be different than 0. It says nothing about that. So that's the part that gets a little bit confusing. So let's do a few more examples to clarify that. So for example, say that we have summation n from 1 to infinity of n over n plus 1. The question is, does this series converge or diverge? We got to make sure that we have a clear distinction between the sequence portion and the series portion. Like in the example of where we had 1, comma, a half, comma, a fourth, these numbers themselves, that's the sequence portion. And in that particular case, the numbers themselves were getting smaller and smaller. They were going towards 0. So the sequence was going to 0. But when we added them up, or we wrote it like this, then we're looking at the series. And that is a different question. That's completely different than looking at the limit of the sequence. Like for example, in this case, the question is, does this series diverge or converge? Is it a finite answer or is it an infinite answer, in other words? So the only tool we have right now, since this is not geometric, we cannot use that formula. The only other tool that we have is the nth term test. So let's apply it. Take the limit as n goes to infinity of the sequence portion, n over n plus 1. Okay, by now we've seen examples like this. The degree at the top is equal to the degree of the bottom. We know this is equal to 1. But what that tells me is, first of all, that it's different than 0. And by the n-term test, if the sequence portion, this portion, does not have a limit of 0, then what is this answer about the entire summation of that sequence? In other words, what is the conclusion about that series? The series will go to infinity. Basically, it diverges because the limit of the sequence was not equal to 0. Think of this as if you were adding infinitely many ones, because each of the sequence terms are roughly equal to 1 after a certain point, and you're adding infinitely many of those, so therefore the infinite sum does not converge. Now, what if we have something like this? Another example. Let's say we have summation of one over n squared plus 1. Can we say anything about the convergence or divergence of this series? Again, this is not geometric, so the only other tool we have at the moment, we're going to learn many more tools later in the semester. At the moment, the only other tool we have is the nth term test for divergence. Notice even from the name of that test, it only works to establish divergence. You cannot establish convergence with this test. So, once again, take the limit of the sequence portion. As n goes to infinity, that goes to 0. So what does the nth term test for divergence say right now? If the limit of the sequence is 0, the nth term test is inconclusive. In other words, the original question, we just don't know. It would converge or diverge. At the moment, we do not know the answer. But later on, we're going to learn other tests. As a matter of fact, we're going to learn many more tests for convergence or divergence of a series. And at that point, once we've learned some of those tests, you would actually say, okay, this test fails. Let me go and apply another test. But at the moment, if you have a question like this on a quiz, all you can say is the nth term test fails and that it's inconclusive. It doesn't tell us anything. How about this one? Summation of 2n plus 1 over n minus 7 as n goes from 1 to infinity. Does this series converge or diverge? Again, as long as it's not geometric, the only other tool we have is this new tool, the nth term test. With that test, we will look at the limit of the sequence portion. We know that that limit should be 2 because the degree of the top is equal to the degree of the bottom. In that case, we know it's different than 0. So what does the nth term test tell us? That the original series diverges. In other words, this sum that was given to us at the beginning of the problem, this sum is infinite. Again, that's what we mean by divergence, especially for a positive series. Divergence meaning it's getting larger and larger without a bound. And if you think about it, it's as if you're adding infinitely many 2's. 2 plus 2 plus 2 plus 2, infinitely many of those, and therefore the sum is not a finite answer. Many people, when they do this question, they come here and they say, oh, we found a limit, right? Great. This must be the sum. But again, you got to be very careful about what you're talking about. Are you talking about the sequence? Because if that's the case, there is a clear limit here. It's a finite number. The sequence portion has a limit. But the series, in other words, when you add up the terms of that sequence, the series does not have a limit. The series diverges in this case. Okay, finally, let's do a word problem utilizing some of the concepts we've learned today. So I found this to be particularly interesting questions because, when people save for retirement, this is exactly what they do. They're investing a fixed amount every month at a fixed interest rate, or of course it could be variable, but for the purposes of this question, we're assuming a fixed interest rate for a period of, in this case, 30 years. So depositing $500 for 30 years, again, $500 per month at 6% interest. And for the purpose of the problem, let's assume that interest is compounded monthly. 6% interest. This is the yearly interest rate, but assume that it is compounded monthly. That helps because if the payments are made monthly and the compounding is made monthly, it makes it for an easier question, and all the questions I ask of you are going to be of that format. So if it's a 6% yearly interest, first thing I want to know is what is monthly interest? Let's first answer that question. The monthly interest is call it R. Interest rate is 0.06. That was the yearly interest rate divided by 12. And let's get that. 0.005. So this is the monthly interest rate. So if you were to keep your money in that bank only for 1 month, basically you would be multiplying it with 0.005 to determine how much interest it has earned during that month. Okay, we want the total money, accumulated sum of this entire investment process by the end of the 30th year. So let's create a pattern here. So at the end of, start with first month. How much money did this person have? Assume money is deposited at the end of this each month. So at the end of the first month, the person deposits $500, and that's all the money that he has. Okay. At the end of the second month, okay, this $500, the previous one has been sitting in the bank for a whole month, so it's going to have a total value of 500 times 1.005. Now, why am I multiplying it by 1.005 and not by 0.005? Because if you multiply 500 by 0.005, you will only get the interest portion, how much interest was earned in that month. But I want to know what is the total amount now of my investment. So if you multiply 500 by 1.005, it's going to then give you the total principal plus the interest that money has earned in 1 month. But remember, a new investment of $500 is made also at the end of the second month. What will happen at the end of the third month? Okay. So the previous month's amount has been sitting in the bank for 1 extra month, so it needs to be multiplied by 1.005. Because remember, what is the effect of multiplying something by 1.005? The effect is you will obtain the final amount, which is principal plus interest that was earned during that 1 month period. So I'm going to take everything from the previous month and I'm going to multiply it by 1.005. So that will give me, so the first term, when you multiply it by 1.005, it's going to become, this term becomes 500 times 1.005 squared. Now multiply the second term by that. And now multiply, oh, there's no third term, so add now the new investment. At the end of each month, we're adding $500. Let's just do this one more time for the 4th month, and then we're going to jump to the end of 30 years, or 360th month. Okay, at the end of 4th month, as a matter of fact, now you're going to see a pattern here. At the end of the 3rd month, look what we had. I'm going to read it from right to left. 500 plus 500 times 1.005 plus 500 times 1.005 squared. At the end of the 4th month, you should have one more term basically, and it's going to look like this. 500 times 1.005 to the 3rd plus 500 times 1.005 squared plus 500 times 1.005 plus the new investment of $500. Okay, let's fast forward to the 30 years, to the 360th month. So from the same pattern, on the 4th month, the highest power was 3. On 360th month, you would expect the highest power to be what? 1 less, right, which is 359. And it's going to go like this all the way to the first few terms. Okay, now once again, looking at this backwards, this looks like a geometric series, right? A is 500, and R is what? To go from here to here, what did they multiply with? They did the same thing to go from here to the next term, all the way to the last term, right? So we have a geometric series, a finite geometric series, and we know the sum of a finite geometric series is the following, based on a formula we learned earlier. So let's apply it. Our A is 500. 1 minus R on the bottom will be 1 minus 1.005, and on the top, 1 minus 1.005 to the k plus 1, which is, now this happens to be the k, 359, so k plus 1 will be 360. Now let's plug this into our calculators and see what we're getting as the answer. Okay, it looks like we're getting 502,257.52 roughly. So in excess of $500,000 is accumulated in 30 years at 6% interest, assuming that the money is earning a fixed interest of 6% per year. Now here's an interesting question to ask. You know, how much was the interest? Because if you were putting $500 into an account for 360 months, which is 30 years, right? So if you multiply 500 times 360, I'm getting $180,000. So in absence of any interest being earned, the amount would be $180,000, whereas we got $502,000. So that difference, roughly in the amount of $320,000 and some change, or $322,000, that is the effect of compound interest. And it would be interesting to make some variations, like what if the investment was $550, or what if instead of 30 years the person could invest for 31 years, and you're going to find some very interesting results. And the bottom line, as they always say, is start investing early, because you are making the most money at the end when you have accumulated a lot of money. You know, into the next year you're making so much more, and even in 1 year, you know, if instead of 30 years, if you could invest it for 31 years, go ahead and plug it, instead of 360, you would plug in 31 times 12, and redo the calculation, see what you would get. You might be surprised.